Welcome to Chapter 5. In Chapter 5, we're going to be talking about trigonometric identities. This is 5.1, our first lesson. I posted the slideshow. You're welcome to go through it on your own. This is just me talking through the slideshow. I thought that might help you out. So the summary of what's in the slideshow, the first thing we have is a definition of a mathematical identity. What does identity actually mean? We're going to talk about the basic trigonometric identities, and we're going to have examples. Actually, we're going to do some examples in the middle and then again at the end. So identity is a concept we use in other contexts. My favorite example for trigonometric identities is a superhero and his alter ego, because we look at them and they look very different, but because we're on the outside reading the comic book, we know that they're actually the same person. Don't look the same, are the same. And that's going to be true for mathematical identities as well. It's two things that are going to look different, but it turns out actually they're the same. In math, the same means they have the same value. A good trigonometric identity to use as an example is sine squared plus cosine squared. That's one side of the identity. It turns out no matter what you stick in for x, the answer is going to be 1. So if you do sine squared of 30 plus cosine squared of 30, you're going to get 1. And it doesn't even matter if you're in degree or radian mode. As long as the x's are the same, you're going to get 1. This will work for, say, 120 degrees. It'll work for pi over 2 in radians. It'll work for pi over 2 degrees, although that's a really weird degree measure. You're always going to get 1. So this makes our trigonometric identity. Sine squared plus cosine squared equals 1. This one's got a name. We're going to come back to it. For right now, though, the basic identities, you actually have learned these relationships, but we didn't call them identities in Chapter 4. These are the reciprocal identities. When we introduced cosecant, we introduced it as the reciprocal of sine. Same with secant, it's the reciprocal of cosine. So these 6 identities are just how you change a function to its reciprocal. Everybody's got one. We also have 2 quotient identities. Tangent and cotangent, you can actually turn into a division of 2 other functions. Since tangent's y over x, sine is y, cosine is x, tangent equals sine over cosine. Cotangent is the reciprocal of tangent, so it's cosine over sine. These identities are the most common identities. You're going to use these a lot. I don't need you to memorize them. I'm going to expect you'll always be able to look at them if you don't remember them, although these 8 we use so much that you probably will memorize them without trying. They'll just come into your brain. When we use these identities, like I said, there's a couple more identities, but we're going to do some examples first, and then I'll introduce the last set of identities. The types of problems we see here are we use one trigonometric ratio to find another value, and the other type of problem we simplify expressions involving trigonometric functions. So let's start with use one ratio to find another. You'll get a problem like this. If cosine is 3/4, find secant. This one's pretty straightforward, relatively. So first thing we need to do is figure out how we're going to relate cosine to secant. And if you remember, we already saw one that was like this in the reciprocal identities. There was a reciprocal identity that says secant is always equal to 1 over cosine. Now that we have this, there's 2 unknowns, secant of theta and cosine of theta, and we have the value for one. We need the value for the other. We substitute 1 over 3/4. That's the reciprocal of 3/4, which is 4/3. So secant is equal to 4/3. This is the same process we're going to keep using. Find an identity with the right ratios in it, substitute the known values, solve for the desired ratio. This one was already solved, so step 3 we didn't really have to do. All right, simplify expressions. This is the one that can be a little more intimidating. There's some intuitive steps here, but I've got cosine of theta and times tangent of theta. We're going to simplify this. The first thing you want to do when you're simplifying is think about how you can change these things so they'll be more similar. Most of the time, if you don't have anything else that jumps out of the page for you, you should try using the reciprocal and quotient identities to turn everything into sines and cosines. So cosine is already cosine. Tangent, though, the quotient identity for tangent is sine over cosine. So that's how we're going to turn tangent into an expression involving just sines and cosines. So we're going to take cosine tangent. We're going to rewrite tangent as sine over cosine. And now we can see the cosines will cancel, leaves just sine. And that's our answer, sine. So cosine theta times tangent theta will always be equal to sine of theta. Doesn't matter what theta you pick. Okay, that was our 2 examples of types of problems. I'm going to show you now the last set of identities. We already talked about this one, sine squared plus cosine squared equals 1. It turns out there's 3 Pythagorean identities. These identities come about because of the Pythagorean identity, but you don't need to be able to derive them. You should have them written down somewhere for easy reference. Occasionally, we need to move some pieces around using basic algebra, like we'll subtract cosine squared from both sides, or we'll subtract 1 from both sides. You need to be prepared for that. But these identities are very useful. Let's show some examples. Example 3 uses Pythagorean identity. It's one of the ones where we have a ratio and we need to find others. In this case, we know that cotangent theta equals 2. We also know that sine of theta is greater than 0. We need to find a value for sine and a value for cosine of theta. All right, so the first thing that probably occurs to you if you look over your list of identities is to use the quotient identity. It relates cosine and sine to cotangent. The quotient identity, cotangent equals cosine over sine. And it's good that you thought that, although it's not going to work in this case, because substitution gives you 2 equals cosine over sine. It has 2 unknowns. We can't solve for cosine or sine because we don't know either one. So we need to look for a different identity. The problem is there isn't one that directly relates cotangent to sine. But there is the identity that relates cotangent to cosecant, and because cosecant is a reciprocal of sine, if we can find cosecant, we can find sine. And this is where the Pythagorean identities become very useful, because they only have 2 functions in them, 2 ratios. So we're going to use the Pythagorean identity to find cosecant, then we can take its reciprocal to find sine, and that's how we're going to find sine of theta. Let's do it. So if we start at the top, 1 plus cotangent squared equals cosecant squared is our Pythagorean identity we're using. We substitute our known value, 2. It has to be 2 squared though. 2 squared plus 1, that's 5. So cosecant squared has to be 5. If we take the square root of both sides, cosecant of theta is going to be either positive or negative square root of 5. Now this is why, when they gave us our information, they told us that sine was greater than 0. And at the time you may have thought, well, why in the world do we need to know that? And this is why. Because we need to know whether it's positive square root of 5 or negative square root of 5. In this case, it's positive. Since sine is positive, its reciprocal has to be positive as well. So sine is the reciprocal of cosecant. So instead of square root of 5, it's 1 over the square root of 5, which you could also write as the square root of 5 over 5. That's the reciprocal identity. Sine is 1 over cosine. Now that we know cosine, we know sine. We know sine and cotangent. We can find cosine using the quotient identity that we found earlier. We stick in the 2 values we know, 2 and 1 over the square root of 5. And now we have this equation, which we can solve for cosine. Multiply by the 1 over the square root of 5 to both sides to cancel out over here. On the other side, we have 2 over the square root of 5, also known as 2 square roots of 5 over 5. Now we're done. We found sine. We found cosine. Problem solved. Example number 4, we're going to simplify using a Pythagorean identity. So here's an expression we need to simplify. Notice they're getting a little bit more complicated. Take deep breaths. Now, the thing I already mentioned is if you don't know what else to do, which this is that case, turn everything into sines and cosines. Cosine's already cosine, sine and cosine are fine. So we're going to turn our tangent into sine over cosine. That's a quotient identity. Now we see the cosines cancel, so I have sine minus sine cosine squared. Since everybody's got a sine in them, I can factor that out. So I factor out the ratio they have in common. That leaves 1 minus cosine squared. So sine times 1 minus cosine squared. Now this right here is a difference of squares, which means we can probably use a Pythagorean identity. Now the original one says sine squared plus cosine squared equals 1. That's not exactly what I need. I need 1 minus cosine squared. So I have to subtract cosine squared on the right here to get 1 minus cosine squared, which means I subtract it on the left, cancels, so sine squared equals 1 minus cosine squared, and so I can replace 1 minus cosine squared with sine squared. Then I can multiply, sine cubed. The instructions for a problem like this will usually say something like, simplify this to an expression involving only one trig ratio. So up here where we've got sines and cosines, we're not done yet. When it's all sines, that's when we know we're done. Keep an eye out for difference of squares. Difference of squares very frequently leads to Pythagorean substitutions, so it's something you want to watch out for. Difference of squares, I should explain. 1 is a square, cosine squared is a square. Difference means subtract. So it's 2 squares being subtracted. Don't forget that 1 is a square, because otherwise you won't recognize these. Moving on, example number 5, we have 2 fractions. Now, anytime you have 2 fractions being added or subtracted, you want to start looking for a least common denominator. Based on what we learned earlier, you might think turn it into sines and cosines first, but since the reciprocal of secant is cosine, you get 1 over cosine, and that makes these fractions way worse, because then you got fractions inside fractions. So we want to go for a least common denominator first, especially because if we multiply these together, we'll get 1 minus secant squared, which is a difference of squares, which will lead to a Pythagorean identity most of the time. At least in class it will. So we need a least common denominator. So we need to multiply over here by 1 plus secant over 1 plus secant. And then we need to multiply the right fraction by 1 minus secant on top and bottom. Now if you multiply the tops, you have to distribute, so that's secant and secant squared. Over here we get secant minus secant squared. And on the bottom, 1 minus secant times 1 plus secant makes 1 minus secant squared. Same thing over here. Now the bottoms are the same, and I can put these together. Secant minus secant is 0, and secant squared plus minus a negative is the same as plus. Secant squared is 2 secant squared. So now I have 2 secant squared over 1 minus secant squared. It's certainly simpler than how I started. I'm looking at this, and the bottom here is my difference of squares. So as I indicated earlier, we're going to use a Pythagorean identity. Once again, it's not quite right in its original form. Tangent squared plus 1 equals secant, and I need 1 minus secant. So if I subtract that 1 over, I've got the secant and the 1 on the same side, but it's backwards. So if I change the sign of everything, the tangent becomes negative, the secant becomes negative, and the 1 becomes positive, and I get negative tangent squared is 1 minus secant squared. So I can replace 1 minus secant squared with negative tangent squared. We're going to have a negative sign in our answer. We're almost done now. We've got 2 secant squared over negative tangent squared. There's no more addition or subtraction, which is a good indication you're going in the right direction. In order to simplify this and reduce it some more, I'm going to now turn it into sines and cosines. So secant is 1 over cosine, so 2 secant squared is 2 over cosine squared. Tangent is sine over cosine, so it becomes sine squared over cosine squared here. Don't forget the negative sign. Instead of dividing by a fraction, I'm going to multiply by its reciprocal. So instead of dividing by sine squared over cosine squared, I'm going to multiply by cosine squared over sine squared. Here the cosines cancel yet again, and I have 2 left on top and sine squared left on the bottom with a negative sign. I shouldn't really leave this as a fraction, so if I have 1 over sine squared, that's the same as cosecant squared. There's our reciprocal identity again. Now I have an expression with no fraction involving one trig ratio. Very good. We've seen a bunch of different examples. You may want to watch this video again, or now that I've explained it to you, you may be able to just go through the slideshow for inspiration. A summary of the blue tips that you saw through the PowerPoint here. The first one is use a least common denominator to add or subtract fractions together. And that means you got to multiply on top and bottom. It seems like a lot, and it's real stuff, but you can do it. Just take deep breaths and remember your basic fraction math. 2, instead of dividing by a fraction, multiply by its reciprocal. We saw one of those as well. It's invaluable. Don't forget to do that. Look out for difference of squares, and anytime you see a difference of squares, you should look for a Pythagorean identity that relates. And if you don't have any other ideas, turn everything into sines and cosines. This should be enough to get you started. Now your assignment, which you have a few days to do, you do need to work on it. Don't put it off to the last day, because then you're going to be like, I didn't get it done. I'll be like, well, did you work on it? No, I didn't. That's going to be our conversation. It's not a conversation we want to have. So you should get started. You've got a few days to complete this assignment. Now, using identities is intimidating until you get the hang of it. You'll get the hang of it. You just got to keep at it. But don't be afraid to ask for help. I mean, I'm sitting here alone all day. Send me an email. Send me a message in the classroom. Uh, also, I suppose I have Hangouts if you prefer, and I have an actual Discord account. So if you need to get in touch with me, decide how you'd like to, and let me know. You can send me partially completed exercises or ask me about questions. I can give you some direction or a prompt to help you get started. Yeah, feel free to work online together. Remember, you need to learn how to do this, though, so whether you're working together or not, don't just write down somebody else's answers. If you want a video chat, we can do that one-on-one, or we can set up a time where several of you get on. You can work together. You can see me. I can post more examples if you think that will help. I can do these all day long. And I'm sure that you can find videos elsewhere or other people who can explain this. So if you want to hear somebody else explain it, I won't be offended. So here's your assignment. Don't do the word problems. We're skipping the section between 16 and 22 because, as I indicated, there are some identities that I'm not making you learn because you're not in honors pre-calculus. Yeah, well, good luck on your assignment. Please let me know if